Good morning, class. Welcome to the MSE 2-for-1 online mode of lecture. I trust that you are all doing well, safe, and healthy. We're all facing a pandemic that is the COVID-19. We're affected in one way or another, some maybe more than the others. Such is our context, and we try to make some adjustment through this virtual learning environment. So in today's lecture, I'm going to cover the topic, the heat capacity of a crystal lattice. More than a month ago, I began the discussion on heat capacity. We are yet to cover two models, the Einstein model and Debye model. But don't worry, I'm still going to review the part on the so-called Dulong-Petit model. So I looked up how it's pronounced, and it's Dulong-Petit. Okay, moving forward, a crystal can be considered as a solid, and the movements of the atoms influence the properties of the solid. What do we mean by solid? We mean to say that the crystal is arranged in a very definite, regular, geometric pattern. Now notice the second part of the statement, saying the atoms influence the properties of the solid. For illustration, recall the simple phenomenon of boiling water. That is understood to be due to the agitation of the constituent molecules of the water. So the molecular movements lead to the rising temperature. The total energy, thermal energy, of a single vibrating atom is the sum of the kinetic energy and potential energy. We call the vibrating atom an oscillator. Now, Dulong and Petit propose that solids are comprised of these oscillators whose total energy is defined using the equipartition theorem. So we're going to review what equipartition theorem is about. So we use the figure below to visualize an atom moving with velocity v in a coordinate system. The velocity has three components along the x, y, z axis, and we assume that the atom is connected to its nearest neighbors by springs. These springs have force constants along the three axes, and what we learned in diatomic chains and monoatomic chains can be useful in imagining this part. The kinetic energy is 1/2 times mass times square of velocity. Considering the three axes, we have three components of the kinetic energy. Likewise, for the potential energy, it also has three components. In particular, our atom has elastic potential energy 1/2 times force constant c times square of position. We see here 3 degrees of freedom contributing to kinetic energy and 3 degrees of freedom contributing to potential energy. Let's appreciate for a while the characteristic of our energy. Energy is shown here to be relative. You have velocities relative to a reference point, also positions x, y, z that are defined with respect to a reference point. Then the molecules are agitated because energy has been absorbed. The vibrations lead to energy transformation into thermal energy. Now, equipartition theorem. Equipartition theorem tells us that in thermal equilibrium, each term in the total thermal energy of a single oscillator would have an average energy of 1/2 k sub b times t. Since there are 6 number of degrees of freedom, so the total energy is 3 times kb times t. This term shows us that temperature is related to the average energy of microscopic modes of disorganized motion per molecule. If our solid is composed of n atomic oscillators, then the total energy will be n times 3 times k sub b times t. Furthermore, the total energy per mole is 3 times Na times k sub b times t, or simply 3RT. What is a mole? A mole is the same number of particles found in 12 grams of carbon 12. Avogadro's number is 6.02 raised to 23, and R is the gas constant, equal to 8.314 joule per Kelvin. We focus our attention now on the heat capacity. How do we define heat capacity using simple terms? Well, heat capacity is the amount of heat needed to raise the temperature of an object to 1 degree Celsius. We take the object's volume to be a constant, so we say in particular heat capacity at a constant volume. In mathematical expression, C sub V equals dE over dt. That is the first order derivative of the total energy with respect to temperature. Substituting the expression for total energy and performing the derivative, we get 3 times R, or 3 times gas constant. The approximate value is 25 joule per mole Kelvin. In year 1819, Dulong and Petit enunciated a principle that the atomic weight of a solid element times its specific heat is a constant. That is the value 25 joule per mole Kelvin. In modern terms, this is simply known as the molar heat capacity. Recall that in the previous slide, we have an expression for the total energy per mole. Then Einstein noticed that Dulong-Petit principle fails badly for diamond. Low temperature studies show that the principle always fails provided the temperature is low enough. By low temperature, we mean those values near 0 Kelvin. So it was found that the Dulong-Petit constant is always too small at some temperature, and it approaches 0 value near 0 Kelvin. However, it should be noted that the Dulong-Petit is consistent with classical mechanics, in particular classical thermodynamics. The question is, why does it fail for diamond? Einstein remedied the problem. He treated the solid as a collection of one-dimensional oscillators. How many of these oscillators, we ask? Well, there are 3 n independent one-dimensional oscillators. Einstein used Planck's theory. It was in year 1900 when Max Planck proposed his quantum theory that oscillators in a solid must have quantized energy E sub n. Then in 1906, Einstein made a deduction based on this quantum theory. If the harmonic oscillators in a crystal have discrete energy levels, as Planck proposed, then they should be all at the lowest level at T equals 0 Kelvin. Okay? They should all be at the lowest level at T equals 0 Kelvin. Very near that temperature, an infinitesimal temperature rise would not be sufficient to promote any of the atoms in the crystal to the next higher quantum state, or the first excited state. Without such promotion, there will be no energy absorption. If there is no energy absorption, then the dE equals 0, or the C sub V dt equals 0. Since dt cannot be 0, it requires C sub V, or the heat capacity, to be 0. The objective at this point is to derive an expression for the heat capacity under the Einstein model. The probability of an oscillator to be in an energy level n obeys the Boltzmann factor. In the following expression, the Boltzmann factor is exponent of negative E sub n over kt, and the probability is written as f of E sub n. We see here that we get the summation of exponent of negative En over kt, where n is from 0 up to infinity. So this will give us a fraction of the total number of oscillators in the quantum state. The average total energy for a solid with 3n number of oscillators can be expressed as follows. E equals 3n times the summation of the product of the probability and then the energy state. Substituting the previous expression, we have the quotient, sum of the product energy state, and then the Boltzmann factor, and then the denominator is the sum of the exponent of negative En over kt. Again, the summation is from n equals 0 up to infinity. Furthermore, we substitute the expression for the energy state E sub n equals n times h bar omega, where h bar is Planck's constant and omega is the wave frequency. So it now becomes a complicated expression. To aid the manipulation of the equation in an easier way, we substitute x for h bar omega over kt. So now we have a more simplified looking expression. And then we perform a bit of a trick here. We get the derivative with respect to x of the sum of the exponent of negative n times x. Furthermore, the exponent can be written as the quantity e raised to minus x raised to n. Then we recall that the expression sum of x raised to an exponent n, where n is from 0 up to infinity, will yield the expression 1 over 1 minus x, if x, the absolute value, is less than 1. So, substituting e raised to minus x for the x, we expect the value 1 over 1 minus e raised to negative x. And then now we perform the derivative with respect to x of the quotient. So we recall what is the derivative of a quotient f of x over g of x. It will be a numerator divided by the denominator. The numerator has f of x times g prime of x minus g of x times f prime of x, and the denominator is simply g of x quantity squared. So we substitute what we got, and we see that our expression has evolved into a simpler version. We notice that similar terms vanish, and now we have 3 times n times h bar omega here, all over e raised to x minus 1. Substituting the value of x, we have 3 times n times h bar times omega, all over exponent of h bar omega over kt minus 1. Then we're interested in the total energy per mole, so we perform that. We have 3 h bar omega over exponent of h bar omega over kt minus 1 times Na, or Avogadro's constant. The heat capacity at constant volume would then be the partial derivative with respect to temperature of the total energy, and we see the final expression here. Why did we do the total energy per mole? Because we're interested in the atomic weight of a solid element times its specific heat, or simply the molar heat capacity, in the same way that Dulong and Petit were interested in the molar heat capacity. The heat capacity is expressed in terms of the Einstein temperature, h bar omega over k equals theta sub E. We now see here two extremes of the heat capacity. At high temperature, the heat capacity is equal to 3 times R, or 25 joule per mole Kelvin, and at low temperature, it approaches 0. I like the following statement. There is reasonable agreement between the experimental results and the Einstein model. It is shown using this graph here. However, also shown in the graph is that as T approaches 0, the heat capacity approaches 0 faster for the experimental values. The experimental values in the graph are the open circles, while the dashed curve represents the Einstein model. An improvement to the Einstein model was provided by Debye. In the Debye model, we treat a range of frequencies from omega equals 0 to a maximum omega. Additionally, we treat the solid as a continuous elastic medium. It follows that in the Debye model, the heat capacity depends on frequency. In the integral equation above, n of omega gives the number of oscillations per frequency. It is also called the number of modes per frequency. Then the C sub E is the Einstein function for a single oscillator. What is a vibrational mode? A vibrational mode can be defined by a frequency omega, energy E, and wave vector k. The number of modes dn within the interval omega, E, and k to omega plus d omega, E plus dE, and k plus dk would then be dn equals n of the frequency, d omega equals n function of energy, dE equals n function of wave vector k, d cube k, since k space has 3 components. Consider one dimension. We have a one-dimensional line of length L equals NA. The number of particles is n, and the particles are separated from each other by the atomic spacing A. Now there should be a boundary condition, that is, the ends of the line must be held fixed. Additionally, another condition is the periodic boundary condition, which means that the atom S and atom S plus N would have the same atomic displacement U. Then we consider one-dimensional longitudinal waves. The resulting normal mode of vibration has the form of a standing wave. Then the exponent of IkNA is the condition for admissible values for the wave vector k. Why should we require this? That's to fulfill the required periodic boundary condition that the atom S and atom S plus N would have the same atomic displacement. It follows that k equals 2 pi over NA, and so in k space, we have regular space points with spacing 2 pi over L. The number of modes in the interval dk in the so-called k space is dn equals L over 2 pi quantity times dk. The number of modes in the frequency range is n of omega d omega equals L over 2 pi quantity times dk. N of omega is the so-called density of states. Now at this point, I want you to remember the wave dispersion relation. It's the relationship between the wave frequency and the wave vector k. The best practical way to determine the density of states is to perform an inelastic neutron scattering experiment and measure the dispersion relation, and then to make a theoretical fit. We extend what we found to 3 dimensions. This time the solid has n by n number of atoms. There are n modes in each spatial direction, so a total of n cubed modes. We still use the letter U for the atomic displacement, and it is shown here having the 3 components of the wave vector kx, ky, and kz. We impose a periodic boundary condition again. What does this mean again? The displacement at x equals 0 is the same as the displacement at x equals L. The admissible values of k are then 2 pi over L quantity times L, 2 pi over L quantity times n, and 2 pi over L quantity times m. The L, m, and n are integers. Plotting these values in k-space, we obtain a 3-dimensional cubic mesh. So a lot of equations in this slide. Using these equations, we capture the phenomenon happening in the crystal. Recall that the elastic waves in crystals are made up of phonons. The contribution of the phonons to the heat capacity of a crystal is called the lattice heat capacity. We saw that the crystal has n of omega, d omega, number of modes in a frequency range. Then the thermal energy of the crystal is given by the integral from omega equals 0 to omega maximum. We assume that the phonon velocity is independent of the polarization, so that we multiply by the factor 3. Notice the modified expression for energy once we multiply by this factor 3 and when we substitute the expression for n of omega. Now, maximum omega is equal to the dBi cutoff frequency, omega sub d. The derivation can be left as an exercise. At this point, we perform a change of variables from omega to z. So the limits of integration will be from 0 to a dBi parameter z sub d. Z sub d is equal to theta over temperature T. Theta is the dBi temperature, and then you substitute the expression for the dBi cutoff frequency to get another equation for the dBi temperature. Then what follows is an expression for T over dBi temperature quantity Q. And thus, after some algebraic manipulation, we arrive at the expression for energy enclosed in the yellow box. The heat capacity is found most easily by differentiating the total energy per mole. We may approximate the phonon energy. How? By letting the upper limit of the integral go to infinity. Finally, at long last, we arrive at an expression for the heat capacity at constant volume under the dBi model. See this expression enclosed in a yellow box?